Welcome to Study Loop.
So now we'll work on problem 138 from chapter 17. So this problem has several parts. Overall, we'll say that as a mass sample of a diprotic acid with a molar mass of 255.8 grams per mole is dissolved in water to a volume of 25 milliliters, and then it's titrated with a saturated calcium hydroxide solution. So before we begin any parts of the problem, we're going to calculate the moles of acid that we have present, as well as the concentration of hydroxide. So first, let's do the moles of our diprotic acid. This is equal to the mass divided by the molar mass. And is equal to 2.18 times 10 to the minus 3 moles of H2A. Now, to calculate the concentration of calcium hydroxide, we need to do an equilibrium table. So calcium hydroxide is not going to completely dissociate in water, so we need to calculate this based on the fact that it is concentrated. So saturated, excuse me. So we do our value here. We can write our KSP is equal to 4.68 times 10 to the minus 6. And so we write our ice table. This is a solid, so it doesn't take it into account. No initial concentration of these. We have plus S and plus 2S and S and 2S. So when we solve for S, or we set KSP equal to our equilibrium term, which is 4S cubed, we get out S is equal to 1.05 times 10 to the minus 2. So to find the concentration of OH, we simply need to multiply by 2. Since we have 2 hydroxide per, or 2S is equal to the concentration of hydroxide. So that is equal to 2.10 times 10 to the minus 2 molar. So this value and this value we'll use moving forward. Now the first part of this question asks us to calculate the two equivalence points, or calculate the volume for the two equivalence points. So all we need to do here is calculate the volume at which the moles are equal. The moles of acid and base are equal, and also when we have 2 moles of base for 1 mole of acid, since we have a diprotic acid for the second equivalence point. So we need 2.18 moles, 2.18 times 10 to the minus 3 moles of base to neutralize the moles of acid. So we do this, we divide by concentration, and we should get volume. And so we get 0.104 liters. Now this here is our first equivalence point. And then if we go times 2, because we have a diprotic acid, we will get 0.208 liters, or 208 milliliters, as our second equivalence point. So that's our answer for part A. Now, if we look at part B, it's asking us the pH after adding 25 milliliters of the base is 3.82. We need to find the value of Ka1. So what we need to do is calculate the moles of base that is in 25 milliliters of that concentration. So the moles of base, or sodium hydroxide, is equal to 0.025 liters times the concentration of hydroxide, which we previously calculated, which is 2.10 times 10 to the minus 2. And then this will give us 5.25 times 10 to the minus 4 moles. So the moles of, this is before the first equivalence point, so the moles of H2A will be what we had initially, which is 2.18 times 10 to the minus 3, minus the moles of base that we've added, which is 5.25 times 10 to the minus 4. And we get this value as being 1.66 times 10 to the minus 3 moles. So the next thing that we have to do is see the amount of conjugate conjugate base that we have. And that will be simply equal to the amount of strong base that we added, since that will be the weak acid, diprotic acid, will be completely converted to the single anion. So then we can do a Henderson-Hasselbalch equation to get the pKa. So we have 3.82 is the pH we're told, is equal to pKa1 plus the log of base over acid, which is 5.25 times 10 to the minus 4 divided by 1.66 times 10 to the minus 3. When we do this calculation here, we get pKa1 is equal to 3.50, and we take the anti-log and get Ka1 is equal to 3.16 times 10 to the minus 4, which is our answer for part B. So now for part C, they ask us to look at 20 milliliters past the first equivalence point with a pH of 8.25 and calculate the Ka2. So once again, we need to calculate the moles of base first. So we know we're 20 milliliters past the equivalence point, so 0.02 liters. And if we multiply by concentration, we can get how much excess base, so how much excess beyond the first equivalence point we have. So 4.2 times 10 to the minus 4 is what we get out. And this is OH minus. Yes. So we can do a similar to what we did for part B. We subtract the acid, which in this case will be HA minus. So at the first equivalence point, we used up all the H2A and everything is HA minus. So that's now become the acid, or the most acidic species in the solution. So at the equivalence point, we had 2.18 times 10 to the minus 3 moles of this species, and we can now subtract the amount of base that we calculated above and get 1.76 times 10 to the minus 3. And the moles of our base in this case, which is not down there, it's not a subscript, it's a superscript, A2 minus is equal to just the same amount of base that we added. And we can do the same thing that we did on the previous page. We get pH is equal to pKa. I'm sorry, pH is equal to 8.25. That's the value that we're given. Now that's equal to the pKa2 plus the log of the quantities we just calculated, the base, which is 4.2 times 10 to the minus 4, over 1.76 times 10 to the minus 3, which is the acid. And so when we do this calculation, we get pKa2 is equal to 8.01. And Ka2, which we do calculate by taking the anti-log, is 9.74 times 10 to the minus 9. That's the value we have for Ka2.